Alright, so let's see. So what's the first thing we're going to do there? Did you guys do anything? Or you just like drawing
Negative 1.
Yeah, so we're going to do
Negative 1. Row 1.
Alright, negative row 1
Plus row 2.
plus row 2.
Equals new row 2.
Good. So put that new thing into row 2 because you want the 0 to show up there. So then I've got, again, you could rewrite the whole matrix if you really, really, really want to. Otherwise, just put what this would be here. So then what do I get here?
Well, your top row's not going to change.
Yeah, top row's not going to change. Here I get 0. Crazy.
4.
4.
Negative 4.
Negative 4.
12.
And 12. Cool. Stop there. Is that cool? Uh-oh, shit. And it's so damn easy. Make one stupid little mistake, and if you do it really early, you're basically screwed. Right? So the way I grade these is show me that you understand the process. That's much more important, actually, right now than the right answer. So the first one stays the same.
Now multiply it by row 1.
Yeah. So now to kill this.
Negative 3.
Yeah, negative 3 times row 1, so I can kill that 3 there. So I'm just trying to make zeros in the right places. Negative 3, 1 plus row 3 to row 3. This here, trust me, dear God, obviously I hope you understand that it helps me. Good Lord. If I'm trying to grade this and you don't give me some idea of what you're trying to do, I have no idea. If you make a mistake and I didn't know what you were trying to do, I can't give you partial credit. I have no idea what happened. So tell me. Plus, when you start to go back, you're like, what did I do? So, as you're doing a problem, if you give yourself little notes, oh yeah, that's what the hell I did. So it helps me and you out. So here, multiply this by negative 3, so I get that. So of course I get the 0 I want there, and whatever the hell else happens.
Negative 4.
Good? 0.
Sweet. Simple.
Now what can I do to both row 2 and row 3?
Divide by 2. Or 4.
Yeah, I can reduce both of them, right? So row 2 I can divide by
4.
and row 3 I can divide by 2. So I get 1, negative 2, 3, 1, 0, 1, negative 1, 3, 0, 4, negative 7, 0. So what's really nice with this one again is I got a 1 there. I was kind of hoping that wouldn't happen, but it's kind of nice when it does, because then I don't have to worry about it. But we talked the other day, if that was a 3, well, it's something I could divide by 3, but then I get all these fractions that I really don't want to have to deal with. So if that was a 3, all I have to do is do,
We'll see.
if there was a 3 there, what's another way to make it a 1?
Make it a negative 3. Add it
So
with
if I had
4
this-
row 3.
So I have the 3 there. I want you guys to get used to this idea. How to make a 1 there really quickly? Well, take row 3 minus row 2. 4 minus 3, I'm going to get a 1 there, right? And it just takes a step of realizing that you're allowed to do that. So very often it's simple, but you're like, I didn't know how to do that. Well, of course you can add, subtract, multiply, you can do all the same stuff you could do with these equations. So if I want a 1 there, hey, there's a quick 4 minus 3 is 1. Alright? And it's not a 3.
But you do the entire row, right? You don't.
Oh, yes.
Okay.
Yeah, if you do 4 minus 3 is 1, negative 7 minus negative 1, negative 6, yeah, cool. Alright, so what can I do now? Now that that is a 1, why is that nice?
Because now you can multiply it by 2.
Yeah, so I can kill this, and that 0 won't screw with my 1. So I got twice row 2 plus row 1. Put the answer where?
Row 1.
That's where I want my 0, so I'm going to put the answer in row 1. Start picking up a little speed here. You guys slow me down if I get anything weird. So that's what twice row 2 is. I don't actually change it. I would put it right back to what it was. That's why I just put it in little parentheses. So what do we get? Do that. So the first one is now 1,
0,
0,
1,
1. There you go.
and 7.
7, cool. And the second one's the one that's not going to change now.
Now multiply it by -4.
So now I'm done with these. And to kill the 4, I just multiply by -4. You guys, my biggest concern is that you are not actually bored, you are actually confused. Let this be easy. This math is so nice and easy if you let it be. I'm just purely going as a 1, how do I kill the 4? Multiply this row by -4 to make it a 0 there. Just trying to make zeros, because that corresponds to doing what in the equations? Making a 0 in here means what happened to the equation?
Killing a variable.
Killing a variable. Alright. It sounds like a protest video. He's killing again. So now I want to take row 2, multiply by -4, add it to row 3, and of course put the answer in
Row 3.
row 3. This is where I want my 0 to show up. So now this will be 0,
-4, 4, -20. So that's 0,
0, 0,
0,
yeah, so 0, 0,
-3,
-3,
-20.
-12. And of course right there I can just,
1 to
1, 4.
beautiful, right? Can I do that? Save me some writing? Is that cool? If you want to do that, that's fine with me. Alright, and then what's really, really crazy, stupid, nice. Why would I not want to kill that one with that one?
Because then you would introduce that.
Because then I lose my 0, right? So this guy is the laser, right? He's got 0, 0. He's very focused. He's only going to affect his last spot. So that's the one I'm going to use. It immediately kills this dude. That's nice. So now I can just add row 3 to row 2.
0, 1, 0, 7.
Yeah, so I get 0, 1, 0, 7. The bottom row is going to stay the same because it's already where it wants to be. And of course, how do I kill this one?
Add it with, actually, yeah, subtract that one.
Yeah, so -1, -4. So then I get 1, 0, 0,
3.
3. So your answer should be 374. Crazy. Now let's do it in the calculator. I use the Twitter feed from the filleted lander.
Pretty dark.
I know. Let's do it. Right. There it is. Like that's 3 kilometers away from its landing on that calculator.
You want to
It's
go
kinda
like that at the end. Just worry about finding your zeros.
So here's how you do this in the calculator.
I'll explain.
Of course, it's good for checking your work.
Yep.
And this is the same as always, garbage in, garbage out. So if you put a mistake of negative in there, put the wrong number in there, you're going to get some weird stuff out. So incredibly enough, we're going to go to where it says matrix. Right there above the -1, the inverse button. So is everybody get to that screen if you're playing along? Now, the way that this calculator works in matrices gets a little annoying, but, you know, just be happy you can do them. This is how I can go do something to a matrix. I have to go right now, and here's math is everything I can do to a matrix. And then edit to where I actually create a matrix. So go to edit. And some of you guys might have stuff here, depending on what your calculator's been used for in the past. My poor little dude's not been used for much, so let's see. So if I go to enter for edit,
3 by 4.
good. Now I want to make it the right dimensions. Now to augment it with that extra one, of course, we make it a 3 by 4. So go ahead and make it 3 by 4. Cool. And the last one is off the screen. And then just plug away. So I got 1 and so forth. So the minute you get it all entered, get out of it. Hit second mode to quit, get the hell out of it. Because if you right now go to matrix and try to do math, it's going to try to put the answer inside the matrix, and then it gets all freaky. It's then the combination of the films, the Matrix, and Inception, and that just doesn't go. So you get the hell out of it, then you go back to Matrix, and now I want to do some math to my Matrix. So you get all this weird stuff. We don't know what that means, but we will today a little bit. That's the determinant. This is something called the transpose. This is the dimensions, blah, 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 blah. So you keep going so you see something that I told you to look for. Exactly. Or you have to take it down to what's called triangular form, upper triangular form, where you got zeros in the bottom, but the other ones aren't zeroed yet. RREF takes it all the way down to only the diagonal has ones, and all the other ones are zeros. So go to RREF, enter, go back to matrix, tell it you want number 1, the A, and then it gives you there. Oh. Cool. So what are we going to do? Because you did. Now, be quiet. I know it's good for you.
So can we multiply two matrices together using that?
Yep. That's great.
So I would just say A times B or whatever?
Exactly. Yeah. All right, so let's talk about... We started talking a little bit about addition.
Well, no.
Subtraction is basically addition. All right, let me show you one thing. If I changed one piece of this, I almost guarantee that I'm going to get something weird. So if I just make this 2, let's see what I get if I row reduce that. Nifty. Now watch this. It's kind of cool. If you get this kind of thing, that might be the answer. Right? So you go to math, to fraction. Let's see if it handles it. There you go. All right. That's kind of nice. So what was it with? Let me define a few. Well, the whole thing wasn't caught. My unpaid intern is not here today. Let's see. All right, so if I ask you to do B plus C, can you do it?
No.
Yes.
Because how big is A?
A is just 2 by 2.
2 by 2.
Oh, yeah, yes, you can.
How big is B?
3 or 2 by 3.
2 by 3. And of course C is also.
2 by 3, yeah.
So the only restriction on adding subtracting matrices is they have to be the same dimensions. The exact same dimensions. Multiplication has got a little bit weirder requirement. So B plus C would just be exactly what you hoped it would be. Just add the damn things direct. Yeah, the corresponding elements get added together. It's like you put that one on top of that one. So you get 4, 4, 16, -7, 2, 2. Okay. So, I mean, if I asked you, what do you think would have to happen if I said, what's 2C minus B? What do you think 2C means?
Multiply C by 2.
Yeah, double C, so you get 2, 0, 18. So you can write that down. So 2C would be 2, 0, 18. -4, 2, 0, right? And then just subtract B. So what you could do there to make it a little easier is just add the negative of B. Or not, I don't care. Whatever makes it easier. You guys kind of with me here? Because negative B is the same thing as plus -1 times B. Okay, that's nothing major. That's nice. That's exactly how you hoped it would be. Multiplication, not quite. And I want to start off with a little bit of a motivation as to why multiplication is weird. I mean, just to finish this out, this would just be -1, -4, 11, 1, 1, -2. What about 2a minus 3b?
Can't do it.
Can't do it. Good. Why can you not do 2a minus 3b?
Because they have to be the same.
Dimensions are not the same. Kick ass. Right. You can't just imagine there's zeros there, because there's not even zeros there. There's just nothing there. Right? Did anybody stay awake thinking about what the universe would look like? What color would it be if it wasn't there? No, Jim. We don't listen. Okay. Alright, let me take all this over here. Well, actually, let me leave this up there for a second. We're going to use these here again later. So, if I have this here, then obviously its matrix would be 2, -1, 3, 5, with the 7 and the -1 attached, right? Another way to kind of represent this is, and this is kind of like where we're headed relatively soon. I want to represent this as a matrix times, how do I want to say this? Vector equals the answer. So what I'm trying to say is I want to pull out, so this is A. That is A. And that's kind of like why I call it a 2 by 2 no matter what. Because the matrix that's in this equation is a 2 by 2. This is added on. So if I put that down there, if I put A down here, 2, -1, 3, 5. This vector has to have X and Y in it. So this is really like I put a 2 times X and a -1 times Y. Is that cool? I could, of course, just say that. That's kind of funny to say it that way nowadays. But 3 times X, 5 times Y. So kind of like introduce those coefficients by multiplying them to X and Y alternately. So that's the idea behind matrix multiplication. It wants to be able to do that. So I can write this in a very, very crazy, useful way. So my X vector is going to be XY. And we normally call this just an X vector. It's like the variable. It has all the variables in your problem in it. So we just give the general name the X vector. And the reason it's called a vector, it's still a matrix, but it's only got, in one dimension, it's only one big. Right? This is a 2 by 1. And I want that to equal the answer matrix, which would be 7, -1. So I want you to realize something. There is no matrix division, but if I ask you to solve this, the first thing you would say is, well, then divide by that, right? So what we're actually going to do instead, we have to learn multiplication first to do this, but what we're actually going to do instead is figure out the inverse of this, and then multiply both sides by that. Because then the inverse of this would cancel this, and I'd be left with xy equals numbers. I know the answer then. Alright, so maybe. So how would multiplication have to be defined so that I end up getting 2x minus y equals 7? 2x plus -y equals 7. So look how multiplication has to be defined if I want this to work. 2 times x, -1 times y. So it's a weird kind of distribution sort of multiplication. So when I multiply two matrices, I multiply the first guy's row by the second guy's column. That kind of thing. I'm sort of skipping a step here at the same time, but that's all right. We'll get over it. But I want this to be, this is really a decent way to motivate you as to why multiplication has to be defined in such a funky way. Is so I can write it like this, in a way that we're used to. So then I can just do like the inverse to both sides and solve it. That looks a lot more like an equation I'm used to. But in order for that to work, multiplication has to work like this. So I recapture these equations. So let's really pull out of this what's important right now. Let me give us a nice, easy starting point here. Let's see over there. Notice one thing about this. What's going to be true if there was another... Now look here, that 2 goes with that x. That -1 goes with that y. If there was another variable here, this currently wouldn't work. So the number of columns here has to equal the number of rows there, so that they actually have somewhere to go. So these are both 2 by 2, right? So the check, this is a little bit, with the 2 by 2, it's a little bit too easy almost. But when I check this, if I'm trying to do 2 by 2 times 2 by 2, let me say this again. Let's see if you guys are with me. The number of columns here has to equal the number of rows here, or else multiplication would never work. What the hell would go with z if there was a z? Nothing. Not even 0. Just empty space, right? The universe never existed. Okay, that's weird. So what has to happen is the number of columns, this number, and the number of rows in the second they have to be the same. That kicks so much ass. So the check is very easy. The middle dudes, when you write the dimension times the dimension, they have to match, or else multiplication is not going to work. And then these guys feel left out. But what's really cool is the answer is going to be this big, 2 by 2 on the outside. So of course for a 2 by 2 matrix times a 2 by 2, it's a little bit lame. It's a little bit too easy. So that's why we're going to do some of these guys here in a bit. So how do we do d times e? Here's d.
Hold on, could you
Yeah.
go back? Okay. So the insides must match.
Good.
And the outside is going to be what again?
The result, how big the answer is going to be.
Okay.
So it gets a little weird. If I had a 1 by 7 times a 7 by 2, could I do that?
No.
Yes.
Yes, because the 7s match. How big would the answer be?
1 by 2.
1 by 2. Okay, guys. And the reason it's nice to know ahead of time how big the answer is going to be, you know how many blank spots you have to fill in. So you don't miss anybody when you're doing this multiplication. So it's kind of nice to know ahead of time how big the answer is going to be.
So the answer is going to be 1 by 2.
For that kind of problem. For this one, it's going to be 2 again. So here I got D and I got E. So when I go to multiply these, on this first one I'm going to just spell it all out. All right? And on the handout I've got, I spelled it all out. Here's how this works. In fact, somebody help me out. What position? So I know the answer is going to be this big. Right? And in fact, I need a lot more room than that. I know the answer is going to be this big. 1, 2, 3, 4. Now, this, if you just are very systematic about it, what I'm about to say is not incredibly necessary, but it's kind of nice to realize this. To get the first row, first column answer, I take the first row times the first column. To get this first row, second column, I take the first row times the second column. The answer that's going to go there. It's beautiful. So if you know how big the answer is going to be, how would I get this answer here?
I don't know. Explain that.
The second column.
Which element is it? Where is it? Which row is it in? It's in the second row. Which column is it in?
Second column.
So I would take the second row times the second column. The answer to that would go there. So here's how this works. If I want first row, first column, I'm going to take these. So 2 times -1 plus -1 times 4. Become a 4. There it is. And then if I want that answer, I'm going to go move to this one. 2 times 2. 4. Look at you go. Plus 5. And then -1 times 4. Let me slow down. So this times this is there. This times this is there. Now I move to the second row. So I'm going to use the second row. This times this. And then this second row times second column gives me that element there. So I get 4 times 2 is 8. Plus 3 times -5, -15.
Why do you have 4 times 4 right there? On the, it's not, it's
That's
negative.
a -1. That one?
I was talking about the one.
Oh yeah, that one. It's a -1 times 4. Shoot. How's that? So then you get, now obviously, my God, please do. You should be able to do that in your head, right? You don't have to write all this out. But I want you to be able to see where that came from So then you get negative 2 plus negative 4, negative 6. I get 4 and 5 is 9, negative 4 and 12, and I get 8 minus 15. Bam. Yeah.
I just got confused by how you did the ordering.
The ordering.
Slowly, one more time.
Yeah.
Yeah,
Yeah,
so
like-
2 times negative 1 plus negative 1 times 4 goes here. So the first row
Oh.
times the first column is going to go in the first row, first column. First row times second column, 4 plus 5 is going to go in the first row, second column spot. It's really kind of nice how it works. So whatever you're currently doing is also telling you where the answer is going to go.
Like 4 plus 5.
Yeah, 4 plus negative 1 times negative 5 is 5.
So you literally,
So it's like a very limited, I'm not going to distribute the 2 to both. I'm going to take this 2 to this 2, and this to this.
okay.
Okay, cool.
Yeah, I see that now.
Yes?
Can we do like a 4 by 3 and a 3 by 4 or something?
Yeah, sure. Alright, so that's that one. Let's do some of these. Which one of these could I multiply? And notice, real quick, what would, here, before we move on, you guys first, real quick, do what ED is. ED is not going to be directly related to that at all. So matrix multiplication is not commutative.
ED.
Yeah.
ED. So once you see how this works, it's pretty quick. It's pretty simple. Right? I don't care how big I make these, as long as the dimensions match up the way it's supposed to, you can multiply. It's pretty relatively easy. So I know these do work. We already did it. 2 by 2 still works. What do you get up here?
Negative 6.
Yeah. So negative 2 plus 8,
Yeah, 6.
and then I get 1 plus 6.
7.
7.
And then I move down to the second row, so now I get 8 minus 20.
Negative 12.
And I get negative 4 minus 15.
Negative 9.
Yeah, so there's absolutely really no relationship. If you saw that, you're like, oh, no. Cool. So they definitely don't have to be equal to each other. Not commutative. So from the ones I have left over from earlier, these here, could I do B times A?
Yeah. No.
No.
You can do 8 times.
Because it would be what? It would be 2 by 3 times 2 by 2.
You have to do 8 times.
So these don't match? No. But you could do A times B,
Or 8 times C.
right? Because what would that be? That would be 2 by 2 times 2 by 3. That works. And how big is the answer going to be?
2 by 3.
2 by 3 is the answer. Cool. Excellent. Now do it. You told me you could. This is absolutely trying to be a beat.
Can't you clear matrices from your calculator?
Well, you can't completely clear them.
Because you weren't working there when they were making this calculator. I wish they had like a slide bar. That'd be nice, right? That'd be crazy.
The new ones do.
The newest do? There you go. They finally figured it out. The backlit screens are nice.
I don't think
on
you'd
some of
allow
those.
people to have them.
What's that?
I don't think you would allow people that have the newer ones.
Why?
Because they're all like touchscreen and like basically they're mini computers.
I don't care. As long as they're not 89, that can actually factor things for you.
Yeah, that's what they are.
Okay, screw that. It's too damn bad.
You can change the keypad on it.
Oh, the Inspire.
Yeah.
Yeah, that's the one that can become anyone. Yeah. All right, so let's see. So we're doing A, B. So we got 1, -2, 4, 5 times 3, 4, 7, 5, 1, 2. All right, so I know the answer is going to be 2 by 3.
Yep.
So then I get
13.
3 plus 10, 13.
2.
4 minus 2 is 2.
3.
7 minus 4 is 3.
13.
12 minus 25, negative 13. 16 plus 5, 21. 28 plus 10, 38. I mean, that's just silly. It's hard. Okay.
Only because my brain wants to go this way, not.
Oh yeah, so it's going to take a little getting used to because matrix multiplication is not the most immediately obvious thing in the world. But since we defined it that way, there's so freaking much more we can do with matrices. They could have defined it some other way, but that would have sucked a lot. Right now, you just got to try. Could I do B times C?
No.
No. Right, because that would be 2 by 3 times 2 by 3. The inner ones don't match. And C times B wouldn't work either.
Can't do any other.
Poor little dudes. They can't
A times C.
work together. Yeah, A times C would work just as well as A times B. Cool. I like it.
So you can only add B and C.
Yeah, you can add B and C, but you can't multiply it. Exactly. Cool. All right. So, I want to get... Oh, let me give you this. I gave this to you earlier.
Right. You have to make it diagonal to one number.
No. As long as you have a 1 and a column with no zeros.
Okay.
So like a Sudoku problem. You need 1, 1. It can be in the row of the column. But don't get wrapped around the 1s, get wrapped around the zeros. That's what always mess me up.
Yes, I am.
Yeah, I get you. I get you.
There it is. Cool. I like it. So here's something else about matrices that get a little weird. Weird. You could maybe, I could certainly write this no matter what B is really. So now we know that these capital letters signify matrices.
Error on this.
Okay. Where?
At the bottom it says step 1 check dimensions. It says for BA, B is 2 by 2, A is 2 by 3, and it says answer will be 2 by 2. It should be 2 by 2.
Oh, all right. Make it a 3.
Understand?
All right. Thanks. Yeah. So on step 1, on number 2, the last thing should be 2 by 3. So now, if I had 5 equals 5, if I multiply both sides by 2, it doesn't matter which side I put the 2 on. In fact, it's weird to even think about that. I don't care if I put the 2 in front of the 5 or the 2 after the 5. Either way, it's 10. But now we realize if I wanted to multiply both of these by some other matrix, I couldn't do this. Because I know that in general is not equal to each other. So it matters the side that you apply a matrix to. So sometimes you want to apply it to the front, and sometimes you might actually want to apply it to the back. So you have to put on the same side of both sides. Does that make sense? Because now we're moving closer towards solving this kind of equation, where we understand this could be a 30 by 30 matrix. So this could be 30 variables, right? This could be 30 numbers. But I could represent it always, I don't care how big it is, I can represent it, bam, like that. So if I figure out a process to solve this always, I could just always use that process. So if I wanted to do something like matrix distribution, so if I said something like, what's B times A plus C? This does work, thank God, but you just have to be, of course, careful based off what we just said. This would be
BA plus BC.
kick ass. So if I had instead A plus C times B,
It would be AB plus CB.
kick ass. All right. So now the placement matters. So we understand matrices aren't themselves numbers. They do have some of the same properties. Right? I can add A and B together to the right dimensions. But this property is definitely different. It's because it's not commutative. You have to be careful about what side you apply it to. Okay, cool.
So you don't have to add the matrix inside the parentheses first.
Oh, you could. Yeah, so what this is saying is if I added this first and then multiplied, it'd be the same as multiplying first and then add. I mean, that's all it's saying. So you could do either one of these as you want. It's just guaranteeing you that you get the same answer either way.
The order of operations still plays.
Yeah, exactly. So order operation still has a place. So in fact, what would this here be? A to the fourth is just A times itself 4 times. And sometimes, depending on what the A is, there'll be a nice pattern to this. So what would 1, 0, 0, 1... Well, what do you think this would be first? Let's do this one first. What do you think that one has to be based off of what we called that the other day? Yeah, it's like 1 times 1. So this is the one matrix that when you multiply it by another matrix, it's going to leave it alone. So sure enough, I get 1, 0, 0, 1. So if I multiply 1, 0, 0, 1 times 4, negative 3, doesn't matter.
You get the
I get that. In fact, if you check it, you get 4, because the 0 doesn't add anything to the 4. Right? And then the negative 3 to 0 doesn't add anything to the negative 3, and so forth. You can see how that kind of works. Let that sink in. So we said the other day that that 1 down the diagonal is called the identity matrix. It's this equivalent of 1 in matrix speak. So if I took, for example, here's where things get interesting. If I took 0, 1, 1, 0, do this real quick for me. Multiply that by 4, negative 3, 2, 7.
Switches it.
Yeah, it flips it.
It's crazy. So this is this here. As you're multiplying this, you start to realize what this will do. It's 0 is 2, and then it's 7, and then it's 4, and then it's negative 3. So just flip it. So this matrix by itself flipped its rows from the identity. So when I apply it to the other matrix, it's going to do that same thing. So we often call this an operator. It operates on this matrix, and what does it do to it? This. So there's only one thing that's happened from the identity matrix to the matrix I'm dealing with. That's called an elementary operation. There's only been one thing that's happened. And what's really kick-ass cool, so what would this do here? How is that one step away from this? What did I do there? That's better, Jeff. How is that one step away from this? All I did was, what did I do to get 1, 1 there? I just added row 1 and row 2. So if I multiply that by 4, negative 3, 2, 7. Let's first try it out. So it looks like I should get what the addition of those would be. And sure enough, you do. You get 4 plus 2, negative 3 plus 7. And then you get 2, 7. So these are really useful. You can start to see how you can break down some giant, ugly-looking matrix into a bunch of commands, a bunch of operations. First switch, then add, then do this, then do that. You can break it down into its little tiny DNA parts. And these would be the little DNA parts. That's what you would do a lot more of in linear algebra. So you ever have to go there. Yeah, that's one big part of linear algebra. Is breaking it down into its little do this steps. Okay.
What would happen if you were to multiply?
Say it one more time.
I was going to say if you were to multiply the normal one, whatever it's called, by the operator.
Oh, if you just multiply this by, you'll just get this.
No, I'm saying the 1 0 0 1 by the 0 1.
And do what with that?
If you multiply them together, which one would it come out as?
Oh, I see what you mean. So if I took 1 1 0 1 and multiplied by 0 1 0 1 0.
1 0 0 1.
And 0 1 1 0.
Oh yeah, so this is a good one. So what happens here? What do you get? You get 0 0. Just do it. You get 0 1 0 1, right? 0 0. So of course, I mean, this is 1 times this. So of course the answer is going to be this. So I thought you were going to say, like, there's something that this wants you to do, and there's something that that wants you to do. Which one wins, or something, right? No, okay. But this one's really, anytime you multiply by 1, you're going to get the same thing back. Yeah, so that's a quick one.
So for the number 5, what was the whole?
So how did we get from this to this? I added row 1 to row 2 and put the answer in row 1, right? 1 plus 0, 0 plus 1, bam. So the one operation I did from here to here was add the rows together and put the answer in the first. So when I multiply any other matrix, a 2 by 2 or whatever it's allowed to do, a 2 by 3, 2 by 20, right? As long as it's 2 by something. You guys with me? Because how big is this? 2 by 2. So how big must this be? 2 by, I don't care. Right? As long as the inner ones match, you can do it. So no matter how big this is, what would this do to it? It would add the rows together and put the answer in the first row. Because that's what happened to this poor little dude. Right? So it's just going to pass that along. It's really kind of cool. It's like a little, how do I describe how I see this? I see this as like little things float around the computer and they just attach and undo this one thing to it. These are little tiny, quick, instantaneous little commands. So if you put a bunch of these together, you get this large matrix that does all of that at once, whatever those little pieces are. So we can look at matrices as operators. So when I operate on another matrix with it, I kind of know what it's going to do to it. Right? So it's a larger, it's a more general view of this multiplication that we're doing. We're actually operating on these matrices. A very boring game, right? Matrix operation.
So that number 5 is basically like saying row 2 plus row 1 into row 1.
Beautiful. And that's exactly what happened when we just multiplied it. Add these together, put the answer row 1, that's what it would be. Cool. All right. So I'm trying to find real quick an easy example. Let me see if I can make one up here real quick. You can do it, Jeff. 5, 5, 3, 3, that would work. Yeah, okay. This is almost too boring, but I won't. Here's one other thing with matrices that is interesting. Sometimes when you multiply 2 together, you get something completely unexpected. So with real numbers, what's the only way I can possibly get 0 out of the multiplication? If there's a 0 in the multiplication, right? So what do we get when we do this? Let's see if Jeff put this together right. No, I didn't. What did I do? I didn't get what I want. Let's see. What did I put in the wrong place? Oh, okay. Gotcha. That's the same thing. There it is. Alright, That's a little boring. It's not quite right yet. Screw it. Is it? No. All right, let me try to make one up on the fly.
Take your time.
Thank you so much. Let me see if I can make one up. They don't give me one, they don't give me one. Nope. Oh yeah, it's supposed to be okay. 5, 2, 3, 3. 5, 2, 3, 3. 5, 2, 3, 3. There it is. Let's try this here. So then we have, that's right, 2, 5. Let's see if that's going to work. Well, we'll get, this is interesting. So, it's not quite what I want. That's right, I'm thinking too far ahead. So there are certain matrices that when you multiply them together, you get 0, 0, 0, 0. That's really weird because neither one of them might be 0. But in this case, what am I going to get when I multiply these together? So 10 minus 9, 1. Negative 15 plus 15, 0. 6 minus 6, 0. Negative 9 plus 10, 1. So the 0 divisor is a little bit harder to come up with on the fly, but this is better. This is where we want to go anyway. I want to figure out, so what would you say about these two matrices then? How do they relate to each other?
D negative. They're inverses.
They're inverses of each other.
D negative.
Right? So if I had an equation like this, if I had AX equals B, where A was this matrix, I could multiply both sides by this matrix and get the answer straight. Let's try it real quick. Let's see if this works. So we haven't discussed yet how to get this. And for a 2 by 2, it's relatively easy. And then for anything bigger, it's not so easy. There's a whole process you have to go through. Well, real quick. Is everybody cool with that multiplication there? All right, and everybody cool with the fact that that means that these are inverses of each other. They cancel each other out, right? They become 1 at the end. So if I had this equation, what you got, John? Let's do it this way. 2x minus 3y equals 3. Negative 3x plus 5y equals, who cares, 6. How do I rewrite this like we did earlier into matrix form, into pure ax equals b form? What's the a going to be?
2 negative
2 negative 3, negative 3, 5.
Yeah, so that's a.
Context y.
Yeah, x, y.
Good, here's xy.
And 3, 6.
And then b would be 3, 6. So here's where you got to be really careful. And this is an easy one to see that you did a mistake. If I multiply this side by the inverse, you can't just put that guy here, of course, right?
No.
2 reasons. You have to do the same side, and if you put it there, the dimensions don't even work anyway. Because again, this is a 2 by 1. So if I put the 2 by 2, I've got to put it in front so they match up. All right, so if I multiply this side by 5, 3, 3, 2. I got to multiply the other side in the same position. So what happens here?
It counts.
So all I did, here's my equation, right? That's my equation. Well, there it is. And all I did was I introduced this matrix right there. Now, why the hell would I use that matrix? Because what's it going to do to this matrix? It's going to cancel it.
Or make it 1 essentially.
It's going to call, yeah, make it 1, and we use this big I for the identity matrix. So you can't use I for any matrix. It's already designated for the identity. So I times xy would just be xy, right? Is that cool?
Yeah.
So effectively, these cancel each other entirely. They make a 1. 1 times this is itself. So whatever I get on the other side is going to be
The answer.
the answer. So of course, what do we get on the other side? We get 15 plus 18,
33.
33, and we get 9 plus 12.
20.
Yeah, so the answer is 33, 21. So if finding an inverse is not really bad, is a decently easy process, especially if they just get bigger and bigger and it's still the same ease, then that is the way to solve these kind of equations. Much better than, doing anything else that we've done before. Yeah.
Yeah, but just to say you always have the inverse of it.
Beautiful, I love it. So there's not always an inverse. And the nice thing is, if there is no inverse, that actually tells you something about what the answer must be. Which is kind of nice. If there is no inverse, I can't do this, but you actually know what the answer is going to be because there's only one solution in that case. If there is no inverse. We'll get there. But I like that. If there is no inverse, what the hell? You can't do this. What's nice is you don't need to.
We still have to find the inverse.
If there is no inverse, no, we
No,
don't.
but we still have to find an inverse.
Yeah, exactly. We still have to know how to find it. Yes.
And so X is 33, Y is 21.
Exactly. Cool. I like it. Damn. All right. No, that's done. So the first thing we'll do next time after questions is we'll talk about how to actually find inverses in general. For larger matrices, it's more difficult. 2 by 2 is easy. You don't know yet. I don't know what to tell you, Chris. We haven't talked about it yet.